Hi folks, this is video tutorial number 5, which is intended for people who are transitioning from the ABAQUS CAE to the 3D Experience platform. Uh, it is very similar to the tutorial 1 where I actually took a steel plate and smashed it against an aluminum tube. Here we have a ball made of steel, which is impacting a plate, uh, given the velocity of the ball and the fact that the peripheries of the plate are clamped. So here's the situation: we have a ball made out of steel, uh, moving with a velocity of 10 meters per second, and it impacts a plate, a plate with these dimensions, 10 meter by 10 meter and half a meter thick, where the four edges are clamped, actually four side faces that are clamped. Now, the, the plate is assumed to be elastic, perfectly plastic, and the ball is assumed to be elastic, all of them made out of steel. It is true that I can solve this problem, the ball, model it as a rigid object, it makes sense, and then the plate as deformable shell, that's fine. However, because the equivalent of this problem was done by that reference using the ABAQUS CAE program, I will do use exactly the same approach that they are doing. In other words, the ball is modeled with solid elements, and the plate is modeled with shell elements. Okay. Now the only thing is that you might wonder, why am I doing this problem? Because later on I will go through similar tutorials, except that there is a damage involved in the plate. In other words, the ball actually pierces through the plate, and this is a good starting point, which does not involve damage. Okay. Now, the material properties for the ball and the plate are given here. The only thing is that the ball is elastic, but the plate is elastic, perfectly plastic, as you can see it. And incidentally, we're solving this problem using the explicit approach, and that's what this playlist is about, trying to replicate the work of other people where they have used the ABAQUS AE program and retrace the steps in the 3D experience, which is uh, basically the ABAQUS solver has the ABAQUS solver, but the interface is completely different. The properties are assumed to be the friction. I want to be using general contact, and the friction coefficient between all involved surfaces is 0.2. Everything else is done default, and the duration of the motion of the ball 5 meter above the midplane until it hits, and then let it go a little bit more is 5 seconds, 0.5 seconds. Now, the only difference between this tutorial and the one that I referenced, the one that I'm trying to replicate its steps, is that that YouTuber goes through some effort in order to partition the ball so that you get a nice mesh, hexahedral mesh like that. But since we're not interested in the deformation of the ball or the effect of the stresses in the ball, I'm going to model this thing very simple four-noded tetrahedral element. Okay, and so here's the situation. This is the mesh that I'm going to get. Notice that these are tetrahedral elements, and this is the standard four-noded shell element with reduced integration, and the size of the shell is given. Remember, it was 10 by 10 by 0.5 meter thick. Size is 100 millimeter. Each side is roughly 100 millimeter, and I'm going to model the tetrahedral with linear tetrahedral. That's why it says three-dimensional, continuous three-dimensional, four-noded. In other words, tetrahedral, with the size being relative. This is a very coarse mesh because we're not interested in the deformation and the stress state of the ball, 500 millimeters. So it's a rather coarse mesh. Okay. So let's go ahead and do that. We go to, it's an assembly problem, by the way, because there are two parts involved. And let me change my unit so that I have exactly what the reference having. So I go to preferences. Let me see. I'm sure you know how to do this, but just in case, so you go to the appropriate tab, which is common preferences under units. So the length, I'm going to change that thing to millimeters. Sorry, meters. And let's see now what else we have. Density, I'm going to change it to kilogram per meter cube. Kilogram per cubic meter, which is right there. Okay, and the stress I'm going to make MPa. Pressure is already MPa. There is something, there is a stress here too, probably. Let's check it out. Stress. Uh, we'll get there. Stress megapascal is already MPa. Velocity is already meters per second. So that's good. These are the things that I want. No problem. All right, let's insert our first part, which is going to be the plate, for example. So let's do insert. Put the cursor there. Right click. Right click. Insert a 3D shape, 3D part. Okay, I'm going to call that thing the plate. Look, right click properties, plate. October 4, 2023. And let me do a copy paste here. Copy, and under instance, type the same thing. Paste. This is so that I can find things when needed. I give it descriptive name. So let's make it. So I go to 3D shape. This is going to be a surface, right? So because I'm modeling a shell element, that being the case, I'm going to, on that horizontal plane, I will sketch a 10 meter by 10 meter uh, rectangle. Let me, okay. So I'll make it centered, although it's not necessary because you're not using symmetry at all. Let's put some dimensions here. So this is 10 meters, 10 meter, okay. And should have changed my scaling. Okay, this is also 10 meters. Yep, okay. And now we're going to fit it just to see it better. So here's the fit. No, sorry, the fit. There we are. And we're going to exit. And we want to put a surface through this. So that being the case, so I have to go to the generative shape design. So let's switch workbenches or applications. Mateo calls them workbenches. So here's the generative shape design. Go there and look for fill, for example, F-I-L-L, and it's going to put a surface through that. So this is already pre-selected. So there's my surface. Okay, good. While we are at it, let's also apply material to this. So what we're going to do is to go to Tools and check for Material Browser. Okay. And actually, you know what? Why don't I create it? Although I have that material, but let me go ahead and create it. So we go to Tools, Material, not the browser, but Create Material, because I want to start from the beginning. And I call this thing Plate, October 4, 2023. This is just the name of the material, okay? And then we say okay. Now it's going to put us in that library. Now it'll take me some time to find out where that, right here, Plate, October 4, 2023. You're going to say apply. And I don't need this. I'm going to put it on that part and a green check mark. And now we're going to input it. So we go here, double click. Okay, so let's see what we got. We have structural, general, general options, density, and for the steel, I think it was 7,850. I'm pretty sure that's what I showed you on the in the slide, second slide. So 7,850 kilogram per meter cube. Yep. And then we go to ABAQUS multi-physics, mechanical, elasticity. Click on the elastic box, and this is two uh, 200 gigapascal, which means either I put another 3 zeros here, or I can retype that thing as saying 200 gigapascal, either way. And the Poisson ratio is 0.3, okay? And then we go to plasticity, metal plasticity, plastic, and it's just elastic, perfectly plastic. So yield strength is, as I mentioned here in this slide, let's see, the yield strength is 500 megapascal. So I put down 500. I don't have to type MPa because it already uses that. And plastic strain of 0, that means this is the yield strength. And that's pretty much it as far as this steel ball is concerned. Okay, so we go all the way to the top, all the way to the top, save everything. And now we're going to insert the second part, which is really the ball. So put the cursor there, right click, insert another 3D part, and I'm going to change this thing to ball properties. I'll call this thing ball October for 2023. Do a copy paste, copy instances, okay, reference paste, and then we say okay, it's right there. Let's go make it. So obviously there are different ways of doing it. What I'm going to do is double clicking on this 3D shape. On that vertical plane, I'm going to sketch. Okay, so let me go ahead and sketch a circle. Let's see now, on the sketch, an arc. How about doing an arc? And I'll make sure that its center is on that vertical line. Whoa, sorry, try it again. So this is the center, starting here. Oh, this is a 3-point arc. Wrong one. Where is that? Here, arc. That's what I want. The circle center there, right there. Let's dimension this thing. The diameter was 4 meters, a huge ball. So let's make the radius is 2 meters. Okay, and let's close this because I'm going to eventually shaft this. Let me close this thing from here to here. Okay, and the center is 5 meters above the midplane. So let's dimension from that point, the center to this line, 5 meters. All right, and exit. Now I want to shaft this thing to get a ball, but notice that I'm in generative shape design because I had to go there to create that surface. So let's switch applications back to part design and look for essentials. Here is the shaft. Select this. Read this thing carefully. It says the sketch 1. Okay, fine. And the axis is Z axis. And it's 360 degrees, so that's good. So there is actually a 3-dimensional ball. All right. And let's create a material for that. So we go here. Where is that? Under tools. Add the material. And I'm going to call this thing ball October October 4, 2023. Let's make it. Here it is. Now I have to find this ball right there, October 4, 2023. And we're going to apply that. I'm going to close this, apply to this part. And now let's go input the properties. So we go there, double click. See now what do we need here? Structural, general, density is the same material, 7850. 7850. By the way, I could have used the one that was already created, but anyway, I decided to make another one because even if you try to use that, because plasticity is given, I will have to remove that plasticity. But when you do that, then the one for the plate is going to go away too. So there are ways of copying things and changing the copies, but it's easier if I just go ahead and plug it in. Where is the other one? Multi-physics, mechanical, elasticity, elastic, and this was 200,000 MPa, 20, or 200 GPa, and Poisson ratio is the same, 0.3. Okay, good. Save everything. All right. Now it is possible to create the mesh independently for each of these parts, but I'd rather go all the way to the top, I'm at the assembly level. And now we're going to go to another application, which is structural model creation. You click on it. It's an MTFEM because I'm going to create it myself manually. Good. And I'm going to include both parts in it. So I check this thing so that both parts are in it. All right, so here is the measure. There is a tetrahedral measure, but I want the linear one right there. Linear, it's called octree tetrahedral mesh. This name is inherited from CATIA, but anyway, there it is. This is what I want. Octree tetrahedral mesh 4-noded. And I select the ball, and I put those numbers that I showed you a few minutes ago. For the ball, I put 500 for the 500 millimeter for the size and 100 millimeter for the sag. So I go here, 500 millimeters for the size, and for the sags, 100 for the sag. And then we say mesh it. There it is. So here both the ball and the part are showing. That's why it looks like that. While we're at, well, let's also create we need to create the properties too. The order, we can do that later, but I might as well do that right now. Where is that thing on the properties? This is the 3D solid section. You click on it, you select this. Notice that the proper material is selected. You say OK. Now let's go mesh this surface. So we go here to mesh again. But I want a nice quad mesh. You click on it, you select that, and let's see what the size was. 100 millimeter offset, we don't need it because it is, yeah. So this is going to be 100 millimeter, which incidentally is 0.1 meter. That's okay. 100 millimeter. And that's pretty much it. So we measure, it's linear. You can see that, linear. Now this is going to be S4, S4R. S4, but we're going to make it reduced later on. Okay, so let's go ahead and do this one too, the property for that. So here on the properties, shell section, you select that plate, and the thickness was half a meter, so 500 millimeter, right? Half a meter, millimeter. Okay, good. The only thing is that let me see for a second. Check this material for some reason It was not selected, so should have been, but let's let's go ahead and do it like that. The different ways of doing it. I don't know why it was not selected, but okay. So let's see now. Plate, ball, right? It's right there. Okay. Now it's selected. Oh no, not ball. Do it again. Not ball. We want the plate. Plate. Right there. Okay. You say all right. Now, if you want to see just the mesh here, just the mesh, not the part, so right click. What is that? Visibility manager. Just show me the stuff. Don't show me the parts. I don't want to see the parts here. Now this one. All right. Let me update the mesh. Surface quad mesh. We did that. Notice that I'm having a problem seeing my mesh, but you know what? The mistake that I made, the size of the mesh, I made it 100 millimeter. So if you go to here, surface mesh, surface quad mesh, the size of the mesh, 100 meter. This whole thing was 10 meter. What I meant to say was 100 millimeter. That's why I'm not seeing it. Mesh. And there we are. Now, let's check it out. Let's check it out. So don't show me the parts. There we are. Whoa, that's too small. Let me check and make sure that actually I wanted this 100 millimeter mesh size. Yeah, that looks good. So, well, maybe it's fine. I'll just leave it the way it is. Okay, so it is there. I couldn't see it before because I meshed it with a single element, 100 meter by 100 meter. So I meant to type 100 millimeter. Okay, that's good. I don't particularly like the size of this because it seems to be a lot finer than what I have here. We'll just leave it. We'll just leave it. It may take a long time to run. I don't think so. All right, let's go ahead and do the rest of the problem now. We go to the mechanical scenario creation. Remember, to do explicit calculation, you have to go to this application, not the structural scenario creation. You go there, mechanical scenario creation. It's going to come and say, what kind of analysis do you have? Well, I have a structural one. There's no reason to do general. You can, but and the mesh is the mesh that I created, the meshes that are created, or the finite element model that I created, and then we say, okay. You just give it time. All right, so notice that we go to procedures and we're going to use explicit dynamics. Explicit dynamic step. You click on it, and the total duration is 0.5 seconds. And I just want to show you that nonlinear geometric effect is included. I don't have to do that. I don't have to include it. It's done by default. And then we say OK. All right. So first of all, let me hide my mesh. So right-click visibility manager, and don't show me the finite element model. Just show me the part. And this is hiding because I probably hid it there myself. So let me see now. Under plate, that surface is probably hidden. I don't need it, but I want to see it too. Yeah, right here. Right-click, hide and show. Okay, there we are. Okay, good. So let's go ahead and clamp the four edges. So under boundary conditions, select the clamp, select these four edges. Okay, let me cancel that. Where is that thing that I brought it up for show? Let me do the following. Let me Right click, hide that, see if it makes it easier to select the edges. Clamp. Okay. Now notice that it doesn't let me pick these edges. It could be because, let me see for a second, why is it? Notice that when I try to clamp this, it won't pick, it'll pick the whole surface, but it won't click the edges. That's because the sketch is showing. So let me hide the sketch. See that when you look at the tree, you can see that the fill is on. You can see that, but the sketch is also on. So one way is to hide the sketch either from here. You see that? Now you can select the edges. You cannot select the edges when the sketch is on the screen. So anyway, so here we have 1, 2, 3, 4. Okay, and then we say all right. So the 4 edges are clamped shell elements. So everything is all degrees of freedom or 0, translation and rotation. Now this piece is under velocity, under a given velocity, not initial velocity. The velocity of it is specified, so that whole ball in the direction negative z, so minus 10 meters per second. And we say, okay, there we are. All right, so we specified the procedure. It was explicit dynamics. We specified the boundary condition, which is clamping these 4 edges, specified the velocity of the ball, and the only thing that's to do is for us to specify the contact interaction. So click on the interaction. First, you define the friction coefficient contact property on the friction, specify. So it's going to be 0.2. I believe it was 0.2. 0.2, yes. Everything else is default, 0.2, that's what it is. It's 0.2, you see that? You say okay. And now we're going to do the general contact. So we go to, there's the general contact. You click on it, select the appropriate friction coefficient that you selected, which was, let me see now. You can do it from the, let me cancel that for a second. What was the name of it? What was the name of that uh, interaction that we defined? Contact property 1. Okay, so that's good. So we go on the general contact. Uh, general contact specify. Oops, not here. Hang in there. Where is the property? Right here. Contact property assignment. None. It says none. Okay, you click on it. Oh, no. No, you're right here. Global contact property. Global contact property. You change this thing to be contact property 1. The one that was, I could have called this thing my contact property, but I left it like that, contact property 1. So I have to select it. Don't do the default, because default there's no friction in it. So you want to go to contact property 1 and you say okay. That's pretty much it. So let's go ahead and let me close this. Save this thing first of all. All right. I think we're good to go. So let me move these things down. So first, let's do a model and scenario check. Make sure if there's anything obvious that's missing. Nope. Do the simulation check. Again, checking for possible obvious mistakes. Say okay. Right now it's doing the simulation check. It's not running yet. Okay. I would say this probably takes about 3-4 minutes to run once this step is done. Okay, that's good. Now, I want to bring your attention to down here on the bottom right corner. It says the time is 5:03 p.m. Okay, so we're going to run it and say okay, because we want to check to see if that wall clock that's going to pop up is actually reflecting correctly the elapsed duration of the simulation. So here is the iteration, and there's a wall clock here. You can see that. So let's see. This seems supposed to be true seconds wall clock. We started at 5:03, and my guess is that's going to take about 3-4 minutes for this thing to run. So far, no mistakes, no obvious errors. Okay, 2,000 steps, 2,089 steps in 20 seconds. Okay. Since I don't want to take any of the time recording this as it is, I'm going to stop the recording now. Once it finishes, I'm going to come back and then we compare the 5:04 with the number of seconds that elapsed here. Okay, so I'm going to stop this. Okay, notice that I came back recording and this thing took about 278 seconds wall clock, which is roughly 4 minutes, 5 minutes, and this is what I've got here. So we started at 5:03 and a half or 5:04, about 4 or 5 minutes. Add to it, you get roughly what we've got here. And it finished, so I'm going to close this. And to do post-processing, this is the initial situation. But then as we go further down, you can see that the ball comes down, okay? Very little stress here, obviously, because there is really nothing there except due to the motion, the inertia probably. But then it hits this at some point. So let me put this thing there. It's hitting it. You can see that because the plate is plastic, it deforms, and this is the last one. So after, at 0.5 second, it's going to stop right there. Okay. Now you can do animation here, and you can slow it down. Let me slow it down. So you click on this clock here, analog clock, and you go to speed. You can control this thing, make it smaller, and you play it. It's coming down. It's going to hit the. It's going to hit the plate. This, of course, is the von Mises stress. These are pretty much in line with what that reference has. Although the contour plots, of course, they look different because they're not exactly at the same instant of time. Now, if you don't like the coloring here, the smooth coloring, you can double click on this thing, and you can say, don't show me the smooth color, just show me the step one, and you can see that it's no longer smooth like that. And the other thing is that if you want to look at the deformation, this displacement, change the displacement. Obviously, right now it's moving as a rigid body. The biggest displacement is for the ball. Okay. Once again, you can change this thing to non-smooth, and then it's going to hit the plate and deforms, right? Remember, the problem with the explicit analysis is that it always runs. Whether it makes sense or not, you have to do some detective work to find out. Now, the other thing that I want to plot, let me exit this thing. The other thing I want to plot is the plot of kinetic energy as a function of time and uh, total energy as a function of time, because this reference from YouTube that I'm using actually plots those two things too. So let me show you how to do that. You go on the plots, on the history plot, and you say, okay, show me show me the kinetic energy total, and then you say okay, or say apply, and there we are. Now, uh, all kinetic energy total. Let me see the total strain energy right there. Okay, and you can decide for yourself whether you like the results or not. But anyway, so this is the essentially replicating the steps in this uh, uh, YouTube video, except that I'm not using the type of elements that he is for the ball. I changed that. Okay. Good luck. After I finished the first part of the tutorial, I realized that I forgot to change the element type. So how do we do that? We go to the uh, uh, to the scenario structural analysis case. Here it says element type assignment. You expand it, double click on it. Notice that the shell element is still S4. I wanted to use S4R uh, because that reference is also using S4R. So we say, okay, and let's run it again. All I have to do is to simulate it, and I'm going to stop the video, okay, and not record all these intermediate iterations, but I'm going to stop it. Once this finishes, I come back and bring up the results, and we see how much different they are. So we say, okay, let's wait for a second before I stop it. Right here, this is where iteration is taking place. When I say iteration, I don't mean equilibrium iteration. This is all the steps that it takes. And now I'm going to stop this and come back in about 3-4 minutes and show you the results. Notice that this is running a lot faster. It's almost 90%, and it took only almost two minutes. So it's faster than the previous one. 94 is almost done. The other one took about 4 or 5 minutes, but this one ran faster. But we want to look at the contour plot and the plot of the history of time history of the plots. Okay, so for the kinetic energy and the internal strain energy. Okay, so this finishes extracting the results. Okay, so let me close this. Let's animate that. This is the displacement, of course. So I'm going to change that later on to 1 mesostress. Has not hit the plate yet. Now it did, and obviously it's going to deform it. You can see that. Okay, let's do the 1 mesostress. Almost zero because the ball is moving as a rigid body. Actually, not quite rigid body, very cool. But you can see that the contours look different. Okay, so this is very important. It's so easy to generate color. You have to do some detective work to see whether these things make sense or not. Okay, that is not the purpose of this tutorial. I want to show you if you can do something in ABAQUS CAE, what are the corresponding steps and the interface and the dialog boxes in the 3D experience platform. Now, let me stop this and look at those history plots, which are here. You go to results, plots. Okay, let's do this, for example, kinetic energy. that didn't change. This may be. Let me do the following. Let me let me get rid of these and do them again. So delete that, delete this, delete that. Okay, let's do another one. Uh, XY plot of the history. Let's say kinetic energy, which was right there. Kinetic energy. You say okay. It didn't change that much. I mean, I didn't change the numbers, but when I look at the actual shape, it didn't change that much. So if you you want to do another one, you go to, for example, another one. Now, uh, if you want to get rid of the first one and just show me the second one, you say deactivate existing plot and change that thing to, for example, uh, what is that? Strain energy, uh, total energy balance. Okay, and there we are. Okay. I think the one that I showed you before was not total energy. It was, I think, total strain energy, something like that. All right. Uh, Good. And that's pretty much it. So this piece is appended to the first video, and you're seeing the whole thing in one package.